When I connect a capacitor to a battery, the capacitor gets energy. Where did that energy come from? It comes from the battery. So that means the battery supplies energy to the capacitor. If I wanted to know how much energy is supplied by the battery, I need to work out the formula for it, right? To do that, let us first look at this general case where I have a box. Now when a charge Q enters this box, the energy supplied to the box is Q times V, where V is the potential drop from the entry point of the charge to the exit point of the charge. So this we know. And we know that this is true for any electrical element. So it's also true for a battery. So let us now look at a battery and let us look at this charge entering the positive terminal of this battery. This battery has EMF E. So if I look at the potential drop from the entry to the exit, it will be equal to the EMF. From the big side to the small side, the potential drop is equal to the EMF. So how much is the energy supplied to the battery? Well, it is Q times the potential drop, so it will be Q times E. So the energy supplied to the battery is Q times E. Remember here that the charge is entering the positive terminal of the battery. Is this even possible? Yes, it's possible, and we use this very often. Every time you take your cell phone and connect it to your wall socket, what is happening? You are actually supplying energy to the battery that is there in your cell phone. So this is used quite often. But many times we would like the reverse, right? We would like to consider the case where the charge doesn't enter the positive terminal. We are looking at the situation where the charge comes out of the positive terminal of the battery. So when the charge exits the positive terminal of the battery, which is what is going to happen here, what is going to happen here? This is the positive terminal of the battery and the current is going to flow like this. So the charge is going to go like this, right? And so the same thing is shown here. And you can see that the charge is coming out of the positive terminal of the battery. And in this case, I'm interested in how much energy is supplied by the battery. This is telling me how much energy is supplied to the battery, which is useful in certain cases, but in most cases, I'm interested in how much energy is supplied by the battery. Let us look at that. So now what is happening? The charge is coming out of the positive terminal. It is entering the negative terminal. So it is entering this way and coming out like that. Well, if this is the direction in which the charge is flowing, then you must look at the potential drop this way if I want the energy supplied to the battery. So I'm looking at the potential drop from the entry point to the exit point. So I'm going to look at the potential drop like that. How much will be the potential drop? From the big to the small, it will be equal to the EMF. From the small to the big, the potential drop will be minus E. So how much will be the energy supplied to the battery? Energy supplied to the battery is Q times potential drop, which is Q times minus E. So it will be minus QE. So this is the energy supplied to the battery. Notice it is a negative energy supplied to the battery. What does that tell you? Energy supplied by the battery, positive energy supplied by the battery. But we already have a formula for that. We can say energy supplied by the battery is Q times potential rise from the entry to the exit. What is the potential rise? Potential rise is equal to delta V, which is equal to EMF in this direction. Here we are talking about potential rise, so that is equal to the EMF. And so Q into potential rise is Q times E. So the energy supplied by the battery is Q times E. Clearly, obviously, because energy supplied to the battery is minus QE. So this is the opposite of that. So it is Q times E. So this is the formula that I'm going to use every time. Energy supplied by the battery is charge times the potential rise, Q times the EMF. Let us now look at the process of charging a capacitor. So I have here an uncharged capacitor C. I have connected it to a battery of EMF V0. I'm going to connect it using wires, but usually the wires we have will not be ideal, so they'll have some resistance. I've taken all the resistance and I've put it here as R. So the rest of the wires, you can treat them as being ideal. The potential drop across the battery from the big side to the small side is going to be equal to the EMF V0. Here we are talking about the initial state. Initially the capacitor is uncharged, so the potential drop across the capacitor is going to be 0. Kirchhoff's voltage law tells us that if we go from this point to this point like this or like that, we are going to get the same potential drop. So this is V0, this potential drop must be V0, this is 0, this is a wire, so the potential drop there is 0. So this potential drop must be equal to V0. And because you have a potential drop across this resistor, you must have a current in this direction, which means in the circuit you have a current like this. So from the bottom plate you have this current that is going to go and deposit charges from the bottom plate and put them on the top plate. In fact, that is exactly what the battery is doing. It is taking charges from the bottom plate and depositing it into the top plate. Okay, so as this current flows, this capacitor is getting charged, and so finally the capacitor reaches steady state. So at steady state, what will happen? No more current flows into the capacitor. Since there is no current flowing into the capacitor, there is no current here, and the potential drop across the resistor will be 0. But Kirchhoff's voltage law tells us that this potential drop must be equal to this potential drop. This is 0, so this potential drop must be equal to V0. And since this potential drop is V0, the charge on this capacitor, Q, must be C times V0. Okay, so in steady state, we know that there is a charge on the capacitor, and so it has some amount of energy. So we can calculate what that energy is. And how did this charge come? Well, this battery took this charge from the bottom plate and deposited it on the top plate. So that means charge Q traveled through the battery. So the battery supplied energy. The capacitor has some energy stored. So obvious question is the entire energy supplied by the battery stored in the capacitor? No, there is a resistor, right? So when you have current flowing through the resistor will dissipate energy. So no, the entire energy supplied by the battery is not stored in the capacitor. There is going to be energy dissipated by the resistor. And the question is, how much energy does the resistor dissipate? How do I calculate that? Well, you know that the power dissipated by a resistor is I square R. For a time t, how much energy will be dissipated? I square RT. Can I use that formula here? Unfortunately not. So let us try to look at this a little more carefully. We are now going to look at how much energy does the resistor dissipate. I am going to look at this at time t. At time t, let us say that there is a current I. At that time, let us say that this capacitor has charge Q. So the potential drop across the capacitor will be Q by C. The potential drop across the battery is going to always be V0. So how much will be the potential drop across the resistor? Kirchhoff's voltage law tells us this is V0, this is Q by C. This must be V0 minus Q by C. Using this information, I can find out what is the current, because I must be the potential drop across the resistor divided by R, V resistor by R. So V0 minus Q by C divided by R. So I found out I. So now what is the problem? I can just directly say energy lost in the resistor as heat is power into time, I square R into T. Unfortunately, this is only valid if I is constant. Isn't I constant? No, because when you have a current flowing like this Q is changing, right? Current brings in charge. So Q is changing. If Q changes with time, this is changing, so this is changing. So potential drop across the resistor is changing with time. But if the potential drop across the resistor is changing with time, then the current is changing with time. And if current is changing with time, you can't use this formula. So then what do I do? You can say for a tiny interval of time dt, you can assume that this charge is going to be almost constant. So you can assume that the current will be almost constant for a tiny interval of time. So for that little time, we can say the energy lost in the resistor is I square R dt. But if I want the total energy lost dissipated by the resistor, then I need to integrate this. Now, is this an easy integral? No, because you see this current is a function of time. And so this integral is going to be too messy. This is too complicated. So I need an easier way to find the energy lost in the resistor. And that's exactly what we are going to do now. Let us now calculate the energy that is lost as heat when we are charging a capacitor. I'm going to start with an uncharged capacitor and I'm going to charge it using this battery of EMF V0. Okay, so this potential drop is V0. Initially it was uncharged, but right now I'm looking at steady state. So in steady state, obviously this is charged and there is no current flowing into the capacitor, no current in the resistor. So the potential drop across the resistor is zero. Kirchhoff's voltage law tells us that the potential drop across the capacitor must be equal to V0. And so the charge on the capacitor must be C times V0. How did this capacitor get this charge Q? This battery took this charge from the bottom plate and deposited it on the top plate. So that means during the charging phase, from the initial state to the steady state, Q is the charge that went through the battery. The charge flow through the battery is Q in this direction, right? So there was a charge of Q flowing through the battery. And once you know how much charge flows through a circuit element, then you can find the energy supplied by that circuit element or to that circuit element. When you do energy supplied to that circuit element, we will say Q times potential drop from entry to exit. When we want the energy supplied by that circuit element, then we'll say Q times potential rise. Here we want the energy supplied by the battery, so it is Q times potential rise from entry to exit, from the bottom to the top. Well, the potential rise is equal to the EMF, so Q times V0. So that is the energy supplied by the battery. So how much energy is the battery supplying? Q times V0. Okay, how much energy is stored in the capacitor? Well, the energy stored in the capacitor is half Q times the potential drop, half Q times V0. Okay, and using this we can find out the energy that is dissipated by the resistor as heat. So the energy lost in the resistor is the energy supplied by the battery minus the energy stored in the capacitor. So the energy lost in the resistor is QV0 minus half QV0. So it is half QV0. Notice that this is exactly half the energy supplied by the battery. Half of the energy supplied is lost as heat. That's quite a lot of heat, right? Now don't remember it like a formula. Derive it each time. Though you're going to see many questions where the energy that is lost as heat is exactly half of the energy supplied by the battery. There will be certain situations where it won't be the case. But this is a very easy idea. This is just energy conservation. So find the energy supplied by the battery, find the energy stored in the capacitor. The difference will give you the energy lost in the resistor. So that means you should be always able to calculate it quite easily. So always calculate this. Don't use this like a formula. Now, notice something interesting. The energy lost in the resistor is half Q times V0. Now, Q is CV0. If I substitute that here, I'll get half CV0 square. Half CV0 square does not have that R at all. It doesn't seem to depend on the resistance value at all. Whether I had resistance of 2 ohms, 3 ohms, 10 ohms, the energy lost is exactly the same. What if I made the resistance really small? Same amount of energy will be lost. What if I made this an ideal wire? Suppose there was no resistor. Suppose I used an ideal wire. I made the resistance 0. What do you expect? Well, it should be the same answer, right? Because if they made the resistance 0, this doesn't depend on the resistance at all. So the answer is that the energy lost in the resistor is still exactly half QV0. But I'm using ideal wires. I'm not using a resistor at all. So then how can I say the energy is lost in the resistor? Let us understand this a little more. To understand how heat dissipation happens, even when you are using ideal wires to charge a capacitor, let us look at this example. So in this example, I have this 10 microfarad capacitor, which is initially uncharged. I'm connecting it to this battery, 20 volt battery, using ideal wires. The moment I connect, this battery will take charge Q from the bottom plate and put it on the top plate. How much is this Q? This potential drop is 20 volts. So the potential drop across the capacitor must be 20 volts. And so the charge on the capacitor must be CV 200 microcoulomb. So instantly 200 microcoulomb will go from here and land up there the moment you connect this capacitor to this battery using ideal wires. Why do people say ideal wires should not dissipate any heat? Because ideal wires have zero resistance. And what is the formula for power dissipated by a resistor? Well, it is I square R. R is 0, so I square R must be 0. I square R is 0, assuming I is finite. So this statement is correct, but it is correct for finite currents. And usually people think current must be finite. Is the current finite here? Think about it. If I join these two, this is 20 volts potential drop, so this is 20 volts potential drop instantly because these are ideal wires. And if this is 20 volts, this must immediately have this charge 200 microcoulomb, right? Q there and minus Q there must happen instantly, which means the moment you connect, immediately there must be charge flow, right? So the charge Q must be transferred instantly. How much is that time? Instant means 0 time. So how much is the current that is flowing? Current is charge by time, Q by 0 because it's instant. Q by 0 is going to be infinite. Q is not 0. Q is not 0. The denominator, time is 0. So the current is infinite. So what? Well, the power I square R will be infinity into 0, right? Infinity square into 0, which is basically infinity into 0. But infinity into 0 is not 0. It is not 0. This is an indeterminate quantity. It can take on any value. Okay, so I square R is not 0 because the current is not finite, it is infinite. So please remember that even ideal wires can lose energy as heat radiation because the current can become infinite. Let us calculate the energy that is lost as heat in this situation. So this charge flows through this battery. So what is the energy supplied by the battery? Well, it is Q times the potential rise. So it is going to be Q times 20. So you're going to get 200 into 20, 4000 microjoules. So this is the energy supplied by the battery. What is the energy stored in the capacitor? Well, the energy stored in the capacitor is half Q into the potential drop. So that is going to be half 200 microcoulomb into 20, which is 2000 microjoules. So how much is the energy that is lost? Well, the energy lost as heat radiation in these ideal wires is 4000 microjoules minus 2000 microjoules, which is 2000 microjoules. This is not a small quantity, right? It's not negligible. There is a huge amount of heat radiation happening in these ideal wires. Exactly half of the energy supplied by the battery is being radiated by these wires. So you have to be very careful about this. Ideal wires can radiate heat out in a circuit like this. Be very careful about that, okay? Because the current becomes infinite. To understand this, let us think about the fact that when a resistor is present, suppose there was a resistor present here, the resistor will make the current finite. So the current will become finite. The moment the current becomes finite, I square R for the wire will become 0 because R is for a wire 0. So ideal wires in that circuit. So if this part had a resistor, the remaining ideal wires will not dissipate energy. So all the dissipation will happen in the resistor. Whenever there is a circuit with a resistor, okay, the energy is being dissipated in that resistor. You can ignore the dissipation that happens in the ideal wire. But if there is no resistor anywhere, then the current becomes infinite, and in that case, the dissipation will happen in that ideal wire. So you have to keep this point in mind, whether you are connecting this capacitor using a resistor or you are connecting it using ideal wires. In either case, there is going to be heat that is lost because the energy supplied by the battery is not equal to the energy stored in the capacitor.